Hello everyone. Today we're going to be talking more about acceleration, in particular free fall. Let's consider this video. This is a high-speed video that was taken in my outer office at 500 frames per second. And it's been slowed down 10 times real speed. Let's take a few measurements. So we set the initial x position to be 0 meters at t equals 0. Now let's take a measurement of how far it falls every tenth of a second. So after a tenth of a second, it's traveled 0.5 meters, 5 centimeters. And after half a second, it's traveled 1.23 meters. There's some errors in this calculation of the distance because everything has been approximated by the spacing of these cinder brick. And we're going to see where that pops up. But let's take a look at the position, each of these positions plotted as a function of time. So here we have the curve of position versus time. And we can see each of these data points that we took, and it looks to be parabolic. If we took the derivative of the position with respect to time, what we're doing is extracting the slope at each position. So here the slope is like this, and here it's like this. And you can see that it's getting steeper with time. Here the slope is quite a bit steeper than initially. And this is represented in this velocity versus time, or v equals dx dt. And it grows linearly with time. And this tells us that the acceleration is constant with time, because we know that acceleration is the derivative of the velocity with respect to time. So everywhere here, if we just have a straight line, the slope is the same at this point than down here. So the acceleration is all about 10 meters per second squared. Let's see if we can be a little bit more precise about this. So let's calculate what the acceleration is. Let's use this position and this time. So we have the distance that it fell to be 1.23 meters. And the time that it took to fall this distance was 0.5 seconds. It's safe to assume that the acceleration is constant over this time period. And so we're going to use the equations that we have. If we look at them, we'll only find one of them that doesn't have a final velocity, and that's this one. X equals the initial t plus 1/2 a t squared. The other four equations, which I'll go to in the next slide, all have v final, so we're going to be using this one, since we don't know what v final is. But here we want to know what acceleration is. So here v initial, since it was being dropped, we're going to assume that this v initial is 0, so we can ignore this term. And so we're just going to end up with x equals 1/2 a t squared. So we're going to rearrange this for a, and we're going to end up with 2x over t squared. And so then we just plug in the information that we know. 23 meters all over 0.5 seconds squared, and we're going to end up with 9.84 meters per second squared. Here we ended up with 9.84, which is a little bigger than the accepted value for gravity, which should be about 9.81, 9.80 something. Is a little bit more reasonable. But you know that this value that we got, just taking some crude measurements from this video that we have, is still very close to the accepted value. So I'd like to go over one more time of these four equations that we talked about in the last lecture that all assume that the acceleration is constant with time. So in this equation we have 1/2 x equals 1/2 v initial plus v final t. And so this one doesn't have acceleration. This one doesn't have x. This one doesn't have v final. And this one doesn't have time. So in each of these equations, there's one unknown that we don't know. And I think that this is an easier way to end up solving these four equations, is to look at what do we know and what do we don't know. And usually we won't know maybe one or one or more of these parameters. Sometimes we may know a lot, maybe 3 of these parameters, and we've got to put some more information together. But the way to solve these problems is by looking at what do we know, what do we don't know, and what do we don't know kind of splits into 2 different things. What do we don't know that we don't care about, and what do we want to find? And so I typically look for what I don't care about in order to help me pick out which of these equations. I think that's a little bit easier than searching through these to find the exact 3 that we want to know. Alright, so let's do some problems. Here we have 2 stones that are being dropped from rest, and they feel no air resistance as they fall. So right away I know that my acceleration is going to be constant if I can assume that there's no air resistance. Stone A is dropped from a height h, and stone B is dropped from a height 2h. If stone A takes t time to reach the ground, stone B will take how long? Alright, so in this problem we are given no numbers. So we can't find a value for the time that it took B to fall. But this is what we still want to find out. What we have to do is find TB in terms of this T that it took A to fall down. So there's 2 strategies. One is to throw numbers at this. And the second one will be just do the algebra. And I'll do both of these for you. And I think that it's actually good practice for you to try to do both of these as well. But end up on a test, maybe you do the one that you're more comfortable with. But still, knowing how to work both of these strategies is a good tool to have in your toolbox. So the first strategy is throw some numbers at this. So we don't know what h is, but let's just say it's 1. That'll make the math easy. T is what we want to find out. This is HA. A fell down 1 meter. Since that's just this H, TA is going to be something that we find out. So let's find out what this TA is. So looking at these, what we don't know and don't care about is V final. So we're going to look for one of these that doesn't have V final in it. And that's going to be this guy right here. So here we go. That x equals the initial t plus 1/2 a t squared. So we want to know t. We know how far it took to fall down. That's this 1 meter that we guessed. V initial, since it's dropped from rest, this V initial is going to be 0. And since it's being dropped, and we're assuming that this is on the Earth, A is going to be G. So here we have x equals 1/2 AT squared. And we just rearrange this, solve for t, so t is going to be the square root of 2x over a. And now we just plug in what we know. So here we got 2 times 1 meter, and then a is just gravity, 9.8 meters per second squared. And what we're going to end up with is 0.45 seconds. Try not to round too much in this case. So this is all for A. This is how long it took A to fall this 1 meter that we guessed for height h. So B is going to fall 2h. So, and this is what we want to find is t for B. So B is going to fall 2, and then everything else is pretty much the same, AT squared. So then TB is going to be square root of 4 over 9.8 meters per second squared. It's 4 because we have 2x, and 2 times 2 is going to give us this 4. Alright, so here we just punch this in, and we're going to find out that this is equal to 0.64 seconds. And this is fine, so we got 2 different times here, but we have to remember what the problem was asking, and so here it's saying if stone A takes time t to reach the ground, how long will stone B take to reach the ground? So what we really want to know is TB is equal to some constant times TA. And so what we want to know is how much longer did it take B, how many times longer did it take B than time A? So here we have TB over TA. And this is going to give us 0.64 seconds over 0.45 seconds. And this will give us 1.42. So if we look back at the question, if it takes stone A, T to reach the ground, how long will it take B? So then the answer will be 1.42 T. So this is how we solved it by making up numbers. Let's solve it algebraically. We start off using the same equation because we want to know the same things and we don't know the same things. So this is kind of the equation for this problem. Plus 1/2, a t squared, and this is going to give us, simplify down to x equals 1/2 a t squared. And so what we know is, let's look at a. So XA is h, and then now we have this 1/2, and now we have a, and then t squared, so TA squared, which we could have just written at t, since we wanted to solve b in terms of that. So this is all that we need to know, and then now we have b. So b is equal to 2h 1/2 a TB, TB squared. And so now we have these two equations, which is pretty much what we did in the last example, but now everything is just variables. We don't have any numbers here. What we want to know is TB in terms of TA. We want to know the same thing. We want to know what TB is in terms of this TA. So what we do is we end up solving this guy for TA. So TA is 2h all over a square root of that. TB is equal to 4h over a. So what we want to know is this TB in terms of this. So what we're actually doing is solving for the C, and the C is this TB over TA. So let's divide these two. So TB over TA is going to be square root of 4h over a all over square root of 2h over a. And this simplifies down a great bit. Since everything is in a square root, I can put everything all together. So here we have 4h over a. And then since this is divided by, this fraction gets flipped. So here is a over 2h. And this simplifies down to square root of 2. So here c is going to be square root of 2. So then this tells us that we're going to have square root of 2t should be the time that it takes b to fall 2h. Alright, so let's work another problem. Here, we're dropping a pebble off of a bridge. So here again we have dropping from rest. This is important because it tells us vi equals 0. And now we're given the distance instead of the time that it took to fall anything. So how many seconds does it take? So we want to find t. And what we also know is that a is this 9.8 meters per second squared. And here we have the distance that it fell is this 29.4 meters. We also know that the initial is 0. So what we don't know and don't care about, that's our v final. So again, we're going to be using this guy. And so how many seconds? We have x equals v initial, that's just 0, so we just end up with 1/2 a t squared, and we're solving for t again. So in fact, this looks a lot like the last problem. So square root of 2x over a, and now we just need to plug a few numbers in. And we're going to get 2.45 seconds. But now we want to know what is the pebble's speed after it's fallen this distance. So there's a couple ways that we can do this, because now we know everything except for v final. So we can pick any of these equations that have v final in it. We could pick this one because we know the distance, v initial, t. We know this one, but I'd like to do one that doesn't have any quadratics. So let's just pick this one. V initial plus a t. And so we're just going to get 0 plus 9.81 meters per second squared times this t that we just found, 2.45 seconds. And so we're going to end up with about 25 meters per second. Here we have a snowshoer falling off a snowbank below and then penetrating into the snowbank this 0.8 meters before coming to a stop. So let's draw this out real quick. So we have some snowbank, that's 3.1 meters. The snowshoer is up here. Then she's going to fall down. So this is the direction of her velocity. And the acceleration is going this way. She starts off with 0 velocity and ends up with a velocity going in this down direction. Then she hits the snowbank. Okay, so here is the cliff. And now she hits the snowbank. And now something else happens, which is that she keeps going down. And she keeps going down another 0.8 meters until she comes to a stop. But she started off with a velocity down, and she ends up with, so this is her initial velocity is down, and she ends up with our final velocity of 0. So if you started off with velocity down and you end up with 0, that means you had to have some acceleration up. So here we had acceleration down. After she hits the snowbank, she had to have an acceleration going up. So in order to work through this with the mathematics, now we have to define a coordinate system. And in many previous problems, we've been pretty lazy about defining that coordinate system, but in this one, it's actually very important that we do. Here we're told that vertically upward is positive. So we're going to draw this as our positive x direction. And so now A is negative, since it's pointing in the opposite direction. V is negative, this V final that she ends up with. And in fact, this distance that she covers is also negative. Because she's going to start off with this 3.1 meters and end up at x equals 0. And then now this is x equals 0, and then ends up at x equals minus 0.8 meters. So let's work through the mathematics. So what we want to know ultimately is this acceleration. So here we have some acceleration, but we can't get that unless we know either time that it took to accelerate this or the final velocity, or the initial velocity in this case. We have to know each of these in this second scenario. So we want to know this acceleration. What we don't know is we don't know this initial velocity. We know this final velocity is 0 because she stopped in this case. And we don't know t. We do know this x is this minus 0.8 meters. So here we have two unknowns, so we actually, three unknowns, so we actually can't solve this. So we have to solve some of what we know in this initial case in order to solve what's happening as she's going through this snowdrift. So probably the easiest thing to work out is looking for her initial velocity, the velocity as she struck the snowbank right before, and we can solve this out. So here we know the acceleration is negative 9.8 meters per second squared, and again it's negative because we said A is down, but we're saying X is up. And we know initial velocity is 0. We don't know time, and we don't care about it. We would like to know this final velocity. And we know that X equals this minus 3.1. Sorry. Because this X is X final minus X initial. Remember this. So here we're taking 0 minus this 3.1, and that gives us this negative number. So if we don't want to know time, then we pick the one out of these that doesn't have time, and that's this guy. So here V final squared is going to be equal to V initial squared plus 2A delta X. So V final is going to be equal to the square root of 2A delta X. And, well, plus or minus. And now we just plug in what we know. So 2 times negative 9.81 meters per second squared times this minus 3.1 meters. If for some reason you ended up with, you accidentally put one of these as positive, you would know that there would be a mistake here because you're going to get an imaginary velocity. So then you need to back up and think about how you defined these as being positive or negative. In this case, we have a negative times a negative. That gives us a positive, so we're fine. So this is going to give us a final velocity of 7 0.8 meters per second if we plug in this. So now we know her final velocity here, and that's going to end up being her initial velocity here. So we just end up plugging this in over here. So now all we need to do is find this A. So this T is the one that I don't care about, but we do know X, so we're actually going to end up using this guy again. So here we have V final squared is going to be V initial squared plus 2A delta X. So in this case, V final is 0. So we end up with V initial squared divided by 2 delta X is going to give us our A, our acceleration. So this is going to be this 7.8 squared all over 2 times 0.8, and we're going to end up with 38 meters per second squared. This is about 4 G's, so falling 3.1 meters is not advisable. Have a good day.